All right, so we have three pure circuits here: pure resistive circuit, pure capacitive, and pure inductive circuit. Now, in our last video, we did say that AC is one whose value and direction change periodically with respect to time. Do you remember? Okay, now I'm not going to be telling you how that here in a pure resistive circuit, voltage and current are in phase, whereas here and here they are out of phase. I'm going to be explaining that in our next video. Now, my focus is to make sure that you understand how your voltmeter, so let me pull this guy out, and your ammeter are connected with respect to DC or AC circuits. All right. Now, if I want to connect my voltmeter, you connect in parallel. So if I connect like this, and I connect like this, you notice I'm beginning to get the reading, right? But to connect my ammeter is different. Okay, you have to connect in series. So I have to cut this wire. Let me cut here, and then I can shift this backward and join them. Okay. All right, you see, I'm beginning to get my reading. So this is how you connect your ammeter. Again, notice that the electrons are flowing in a back and forth manner because we are dealing with alternating current. Even if I switch to the conventional mode, excuse me, in our last video, I did explain the difference between real current and conventional current. So here we have conventional. Notice that it's in two directions, forward and backward directions. Is that okay? All right. Okay, now we have already covered this. Okay, we've covered this. Please watch the video. We are here right now, and I've also covered close to 30 questions, UTME/SSCE questions with respect to AC. All right, now I need you to know that in AC, you don't just say current is this, voltage is that. You have to tell us the one you're talking about, because it can be instantaneous current, okay, it can be peak current, it can also be the RMS current. We also have the average current, but of course average current over one cycle is 0, so we don't often talk about this guy. Now, instantaneous current, that's the current at a particular point in time or at a particular instance in time, okay, is given like this. The relationship between instantaneous current and the peak current is this, sine, then the phase angle. Now, if I know that theta is equal to omega t, all right, and that omega is equal to 2 pi f, that means I can as well rewrite this, okay, peak current times sine omega t. Okay, I can as well write it like this, peak current times sine 2 pi ft. Excuse me, they are just the same thing. Is that okay? Now, this guy, the peak current, you can as well write it like this, I sub p. Some people also write it as the amplitude current. It's the same thing. You can as well write it like this. Excuse me. You can as well write it like this, the maximum current, like this. All right? And the relationship between the peak and the RMS value is the RMS value times root 2. You can also write it like this. Don't worry, I'm going to explain these two using the graph. Then RMS value also peak over root 2. You can write it like this. Now, the graph is like this. Let's say we have our current here, and this is time. Okay, much later I'll be telling you that sometimes we can as well put theta here. All right, so over one cycle we have like this. This is one cycle. That's 360 degrees or 2 pi radian. Okay, so here, this point, is the peak value of the current. Now, if you are discussing voltage to be the same thing, now listen, for V, we also have V naught okay, VRMS. It can as well be E, that's EMF, E naught, and then EROMS, the same thing. All right, so whatever we do here with respect to current, we can as well match it with these guys down. All right, so any point I touch on this graph, any point I touch is instantaneous. All right, so at this point it is 0, at this point it is peak in the negative direction, this point it is 0. Okay, so from here to here is half a cycle, whereas from here to here is 1 cycle. Now let me explain the relationship between time, okay, and the phase angle. So let me draw the graphic in. We have this, okay, time, second, and then here current. Okay, so over 1 cycle we have this. All right, now when t is equal to period, that is time from here to this point, okay, the time it takes this to go from here to here is period. Okay, that means the phase angle is equal to what? 360 degrees, which is the same as 2 pi, okay, rad. Is that okay? Now I also need you to know that period is not just equal to 1 all over f. Period is also equal to 2 pi over omega. Do you remember? Okay, let me prove it. I think I should write it down here. You remember that omega is equal to 2 pi f. So if f is equal to 1 over period, that means we can write like this. Omega is equal to 2 pi 1 all over period. Is that okay? Okay, that means we can write period. We can say period is equal to 2 pi over omega. So take note of these two formulas for period. Very, very important. So let me also write along this same line. Okay, so when t is equal to period, that also means that period is equal to 2 pi over omega. All right, so let's continue. When t is half a period, all right, the phase angle is 180 degrees, which is the same as pi rad. Okay, that means half a cycle, right? Okay, that means that period is also what? That's this divided by 2. So this will give us pi over omega. Do you remember? If I divide this by 2, so these 2 will cancel this 2. You have this, right? So when t is equal to period over 4, okay, that's 1/4 of the period. That means 1/4 of a cycle. That means phase angle is 90 degrees or pi over 2. You must understand this. It's very, very crucial. All right. Okay. So this also means that period will be equal to what? Pi all over 4 omega. All right. Okay. Okay, so if you actually understood what I just explained, that means you can answer this question. It's a jump question. The instantaneous value of the induced EMF as a function of time is this. Okay. All right, is this, where E is the peak value of the EMF. The instantaneous value of the EMF, 1/4 of the period is what? So they are saying 1/4 of the period. So that means T is equal to 1/4. That is period over 4. You already know what that means. So at this point, that means we have 1/4 of a cycle. That means theta will be equal to what? 90. That's 360 divided by 4. That will give us 90 degrees. Did you get the point? So that means I can actually write this like this. E is equal to E naught sine, okay, and then plug in what theta is, which is what? 90 degrees. So sine 90 will give me 1. Okay, so that implies that instantaneous EMF is equal to the peak EMF, because multiplied by 1 will give you the same thing. Did you get the point? It's as simple as that. Just take note of this guy. Very, very important. All right. Okay, let's take a look at these other questions. In the curve below, PQRST represents an alternating voltage of frequency 50 Hz. The time interval between point P and R. Okay, so they are asking us of this point P and point R. And this is half a cycle. Remember, one full cycle will be from here to here, which is 360 degrees. So half a cycle, that means T will be what? Period divided by 2. And that means that theta will be equal to what? 360 divided by 2, which is 180 degrees, or pi rad. Do you remember? Okay, so now we are given frequency. And I know that period is equal to 1 all over frequency. That means 1 all over 50. Okay? But this is what I'm looking for. T is equal to half of the period. So that means the T we are asked to find, T will be equal to what? Period divided by 2. But we know that period is this. So it will be 1 all over 50, okay, divided by 2, which is times 1 all over 2. And that will give us 1 over 100 seconds. Did you get that? So the correct option is C. Understood? Now the next one, an alternating current, this has the waveform shown above. The length ON is equal to dash. Okay, so again, don't forget that along this line, okay, we are considering what? Time. All right? But of course, there's a relationship between time and the phase angle, theta. Remember when we discussed wave? The one of wave was like this. Here we had V, T. Then sometimes it can as well be X, T, because X has to do with lambda. Remember wavelength. But here we don't talk about wavelength. We either talk about the phase angle or the time along the horizontal. Is that okay? All right. So we are asked to find the length of ON. So of course they are talking about time, ON, from here to here. So what will be the time when we have the period? That's the time made over one cycle, because ON is one cycle. That's what they are saying. Is that okay? All right. So if I know from what we had established earlier on, we said that period is equal to 2 pi over lambda. Do you remember? Because I'm looking at the options. So I record this guy. Now I also know that, so I can put down this. Let me make space. All right, so I've been able to make space. Now, if I know that period is this, all right, all I need to do is to write the same equation. Okay, I is equal to I naught sine omega t. But now I know that this t, small letter t, look at it here, t is period, because we are asked to find from 0, from here to where? To n. Okay, so t, small letter t, is equal to period. So that means I can rewrite this. I can have this. Okay, omega what? Capital T. So t is the same as capital T. And okay, so t is capital T and is the same as 2 pi over lambda. So assuming the question said we should find OL, that's half. So that would have meant that T will be half. Okay, half of the period. And of course, half here will cancel, and then you have pi over omega, right? That's for half. Then quarter, of course, like that. But the question here says ON, that is one cycle. Is that okay? So the correct option is 2 pi over omega. That is this option. All right, so this is where we are going to stop. Let's answer these questions. Pause the video and give the first one a try. So an alternating current of RMS value 20 amperes will have the same heating effect as a direct current of 20 amperes. True or false? It's true. We already said that the RMS value is equivalent to the DC value. Okay, you remember the definition we gave here? So the RMS current is defined as the steady current which would produce or dissipate the same heating effect, all right, per second in a given resistor. Now take a look at this. It is the DC equivalence of AC, or the effective value. Very, very important. Okay, so it is true. Now the next one, an alternating current which varies from 0 to a peak of 50 amperes has an effective value of 25 volts. True or false? Pause the video and try it. Okay, so it is false. Now we already know that the RMS value is equal to the peak value divided not by 2, all right, not by 2 but by root 2. So if we have 50 as the peak value and then we divide by 2, that's when we get 25 now, right? But here, if you divide 50 by 2 by root 2, you're not going to get 25, so it's false. All right, this one, in measuring high frequency AC, the instrument used is the dash. Now we have 3 instruments basically that you should take note of: the moving iron ammeter, the hot wire ammeter, the moving coil ammeter. Then this one can be anything. All right, now the moving coil ammeter is solely for DC, so it's already ruled out. We are left with option A and option B. Moving iron ammeter, all right, is used when the frequency is low. When the frequency is low, all right, because this guy works based on the magnetic effect of current, whereas hot wire ammeter works based on the heating effect of current. All right, if current flows through a wire, the wire gets hot and eventually expands, and of course it impacts on the pointer. So this guy is used, or is most effective, when the frequency is high, because it does not depend on frequency. All right, it makes use of the heating effect of current. So the correct option is B. Okay, the final one: when a certain AC supply is connected to a lamp, it lights with the same brightness as it does with a 12 volt DC battery. The RMS value of the AC supply is what? Is the same thing, the same 12 volts. Remember that the DC equivalent of AC is the root mean squared value. Okay, all right.